Here is a demonstration of the quicksort algorithm. So I have my console up, we'll type in SML, and in this directory I have uh, my project 2 in here, dot SML, and we'll bring it up. And in here, there is the quicksort function, and I'm going to use 4132 as a example. It's a short little example. Let's see, 4132, that's definitely what I want to use. But it's a short little example to show how quicksort works here, just as a demo. And quicksort looks for a pivot. It sorts things that's less than the pivot in one list and things that are greater than the list in another list. And it uses the divide and conquer principle to sort the list in ascending order. So there's a kind of a look-see of how it works. Here on the left, I have a breakdown of the code in the ML language. Some new things are being introduced here as far as the ML language is concerned. Some new things here is the let, in, and end keywords. The let block introduces a block of local definitions, like in this case, a partition helper function, along with the definition of local values and even types that you want to use temporarily. And then it has the end block here where I call quicksort, and I use the lists and variables that I defined up in the let block area. And then the end basically marks the end of the whole let block. The advantage of using that is just to keep the code clean and modular, organizing the logic, avoiding name clashes, and just to make the code more readable, especially with multiple calculations depending on shared values. At a real high level, what this quicksort algorithm does is it uses pattern matching here again with the let in and end blocks. And with pattern matching here, I can look at two base cases. One's where you've got a list, an empty list, and that's going to return, that's already sorted. There's another base case here where you have just one item in the list, so that's already sorted. And then the last pattern matching here is something that has two or more elements. So that's where you've got to actually run through here the quicksort algorithm and use the partition. If the list is empty or it has one item, then it's already sorted. As I said before, you just return. But if it's two or more items, we come in here, we choose the pivot, we grab the first element in the list and use that as the pivot, and then we call the partition helper function by going through the rest of the list. We put items that are less than the partition into the smaller list that I call smaller. I prepend it actually. If you're greater than or equal to the list, or greater than or equal to the pivot, we end up putting that in the greater than or equal part of the list. And then basically in the end expression here is where the quicksort is actually called in a recursive manner, where I do a quicksort call on the smaller list that was built up here above, and I concatenate that with the pivot, and then that gets concatenated with a quicksort call on the greater than or equal list. And basically here in this expression, we're combining the sorted smaller part, then the pivot, with the sorted greater than or equal part using the @ concatenation operator. And for the example that I did with 4132, here's a kind of a tree that you can follow through. If you stop the video, you could kind of follow through this, and it kind of shows you how each part is built, what goes into the smaller list, which parts go into the greater than or equal list, and how everything is concatenated at the end to give you the final sorted list 1, 2, 3, 4. And that pretty much summarizes the rundown of the quicksort algorithm. Thank you for your time.